No, classes not so much, but you guys are wonderful. All right, so today we're going to talk about continuity over an interval, and the definition of the continuity over an interval is a little silly almost to me. A function is continuous on an interval if the function is continuous at each point in the interval. Now, can we actually prove that? Can we prove every point in an interval? Not real, definitely not individually, right? Because we could never possibly, even if we're like between the numbers of 0 and 1, right? There's infinite numbers between 0 and 1. There's 0.5, there's 0.9, there's 0.99, there's 0.999. There's so many others in between, right? There's infinite numbers. So you cannot prove every single point in this case. A lot of these questions don't show up as like free response questions where I have to write out the proof, whereas on the continuity at a point, they're more likely to be on the free response questions. But they do show up where you have to decide on an interval there. So the following functions are continuous on all points in their domain. So let's see. So domain goes in that blank right there. Let me get my pen. Domain. So if you see a polynomial, an exponential, a rational, radical, logarithmic, trigonometric, they are all continuous on their domain. And on the next slide, we're going to look at what those domains are for these. So if I see something like a quadratic is a polynomial. It's just all real numbers is your domain. So a quadratic is continuous. It can be common knowledge that if you have a quadratic, that is a continuous function. So you don't have to prove it. It is a fact there. So what we have here, if you have a polynomial, it's always all real numbers. And examples of polynomials are things like f of x equals 3x to the third minus 2x plus 1, or g of x equals x minus 4 squared, right? Polynomials are just some sort of expression where you have x raised to powers. Technically, I guess things like y equals x, that's not a polynomial because it doesn't have more than one expression, but it still falls into that category. It's just a line. It's continuous everywhere. Exponentials, those look like this. It could be like f of x equals 2 times 3 to the x power, plus 2 maybe even, right? But the piece that makes it an exponential is having that 3 raised to the x power, right? That makes it an exponential. That is always continuous. Another one that you'll see a lot is something like negative 5e to the x. So that e to the x part makes that an exponential. Exponential domain is all real numbers for that. Both of those types of functions are just continuous everywhere. If they ask us about it, we can just say continuous everywhere because they're always continuous everywhere. For rational equations, these are fractions. Rational starts with ratio. A ratio can be written as a fraction. So it might look something like this. F of x equals 2x minus 3 over x squared minus 2. That's a rational function. Now, these are continuous everywhere except places where the denominator is equal to 0. And we really already looked at that just recently, right? Because that's where we have our holes in our vertical asymptotes. So rational functions are continuous everywhere except for those holes in vertical asymptotes, which are places where the denominator equals 0. Okay? A radical is a root. However, notice I put over here even roots only. So it is a square root, a fourth root, a sixth root, not a cube root or fifth root or seventh root. Well, those are also radicals, but they just have all real numbers for their domain. I guess I could have put another little thing for that. The one you see the most often is the square root, though. That's the big one that we're going to see. So this question, this one might look something like this. F of x equals the square root of x minus 2. Okay. I'm going to use a fancy word here. The radicand. I hope I spelled that right. I think I did. Is greater than or equal to 0. Whatever is underneath that square root is called the radicand. Okay, so it's what's under the square root. You might want to make yourself a little know that. Radicand is what's under the square root. Has to be greater than or equal to 0, because what happens when you have a negative under the square root? Imaginary numbers, those can't be graphed. The graph does not exist at those points. Oh, I've forgotten this one. What do we call the stuff we're taking the log of? I've forgotten it. I know it's not coming to me. Let's see if I put the answer here. Oh, I did. Argument. That was smart of me, wasn't it? There we go. I may have messed it up where the other stuff's not there yet, but the argument. So the argument. Oh, shoot. Is greater than 0. Not greater than or equal to. You cannot take log of 0. So this may look like this. Something like f of x equals natural log of x minus 4. And so the argument would be, in this case, x minus 4. It's that stuff inside of the log. I'll have to ask this Fisher what they're up to over there. Okay. Everybody good there? All right, trig functions. Sine and cosine are all real numbers because those are just our waves, and they keep on going forever, right? They have no discontinuities. But tangent, secant, cotangent, and cosecant all have vertical asymptotes. The way that I remember this is that, okay, tangent. What's another way I can write tangent? What's one of those trig identities? Sine over cosine. It is sine x over cosine x. What is secant? One over cosine of x. So the bottom cannot be 0, right? Because the bottom of a fraction cannot be 0. So cosine of x cannot equal 0. If you think about that unit circle here, we got 1, 0, 0, 1, negative 1, 0, and 0, negative 1. Okay, if we think about that unit circle, cosine is at my x-coordinate or my y-coordinate? It is my x-coordinate. So we're looking right here. This is at pi over 2. Cosine equals 0 there. We're looking right here. That'd be 3 pi over 2. That's right here. Then it'd be 5 pi over 2 and 7 pi over 2 and so forth. The answers for like the places they're spaced out by half of the circle. How far is half of the circle? Pi. That's why we got the plus pi k right there for that. So pi over 2 plus pi however many times, right? Okay, cotangent. For cotangent, what is cotangent? How could I rewrite that one? Cosine x over sine x. What is cosecant? 1 over sine x. So for both of these, sine of x cannot equal 0 because sine is in the bottom. So if I'm looking at my unit circle, sine is the y-coordinate. That's here. It's at 0, and then it's at pi, and then be at 2 pi, and 3 pi, and 4 pi, and 5 pi. So they just write it as pi times k, where k is an integer, right? You can plug in any integer, which is whole numbers and their negatives, and that would give you your discontinuities there. I know in pre-calc, it kind of messes up a little bit having to do that plus 2 pi k. Like, that was always a struggle. It was one of the harder things that we had to do. But sometimes you don't actually have to give, like, the infinite answer. You just have to tell a place where it's discontinuous. So it'll be okay just to, like, if you think of the unit circle where sine 0, oh, these and these don't work. Okay, questions? These are important for us to remember. This kind of sums up half of pre-calculus right here, right? Like every new thing that we learned, we had to learn all those domains with them there. So this is sort of a summary of all of those things. I always said whenever I was in school, like, I really understood Calc 1 whenever I had to use the stuff again in Calc 2. Like, when you got to do it a few times, it starts to stick a little bit better. So hopefully things like that domain will come back around pretty easily. Here, you may have a question that looks like this. Is f of x equals 1 over x minus 1 continuous on the interval from 2 to infinity? Justify your answer. So, what type of function is this? That list we just looked at. This is rational, right? So we are looking at a rational function. Okay. And on that slide that we just looked at, for rational, it said the denominator is, I put equal, but I really should have said not equal, shouldn't I? Like, if we're telling the domain, I should have said not equal. Squeeze in a not. So denominator is not equal to 0 there. So, f of x is a rational function therefore it is, oh, I really shouldn't have done that. What word have I used? It's not good. I really shouldn't say it. You could get by with it on this problem. It would be okay to say it. But it's better. What is it? What do I mean? I mean F. So call it F. Every time. Just never write the word it on your free response answer. Once again this year, grade and AP exams this summer. I can't tell you how many kids lose credit because they just call it it. And then when you say it, it may or may not be clear what it is. And it has to be clear. I think you'd be okay because it pretty clearly refers back to either f or the rational function here, which are both sufficient to talk about it. But just don't write it. Don't ever write it because there's so many times that it goes wrong. So f is a rational function. Therefore, f is continuous for all real numbers except what number? X equals 1. Because x equals 1 gives us 0 in the denominator. Okay. However, what are they asking us? 2 to infinity. Is 1 in that interval? It is not. So, I'm going to say since x equals 1 is not on the interval to infinity, f is continuous. On the interval to infinity. Now, there could be some different wording here. The key that you have to have is you need to say this is rational, which is continuous everywhere except for 1 in some form or fashion. Your wording could be different, but you got to have that piece of information. Then you got to say 1's not on the interval that we're looking at, so f has to be continuous, right? Your phrasing of things can be different than what I have, but you have to have those pieces of information. And if you see justify your answer, that means you can't just answer this with a yes. Okay, it means you got to give some sort of reasoning for that. Now, you'll have some of these on multiple choice questions where you don't have to justify yourself. You just pick the right answer and you move on. But for ones that are free response, you're going to have to give an explanation, which I know I feel the same way. Entirely too much writing for a math class. We should just be dealing with numbers, but because numbers are better. But we got to be able to explain ourselves. Okay. All right. These don't say justify your answer. I didn't make a multiple choice, but I'm going to act like these are ones we don't have to justify our answer for. So we've got the graph below. It's made of a line segment, a point, and a part of a parabola. Is G continuous on the interval from 4 to 8? So when we're looking at the interval from 4 to 8, I like to think of putting myself some vertical lines on this graph. Right here's 4. We're talking about from here over to 8, which is here. Is my graph continuous on that interval? Yes, it is. Okay, what about from -2 to 8? -2 would go all the way over here. The 8 would still be over here, so ignore that middle line, right? We're talking about most of the graph here. Is G continuous there? No. What point is giving us trouble? That 3, -6, right? So this one would be a no. Let me add another question. You don't necessarily have to write this down. Is G of X defined on the interval -2 to 8? Okay, what's it mean for it to be defined? There, like it has an answer, like you get an answer out, right? So it doesn't have to be continuous. It just has to have a graph there. Do we have something at every point? These should have arrows on the end. They don't, but they should. We got something everywhere. The trouble point again is at 3, but the graph is still defined at that point because we got the dot that fills it in. So this would be a yes. It's defined everywhere. It's just not continuous. Okay, questions? Okay, 4-3. Given the functions f and g shown below, is f of g of x continuous for all real numbers? Okay, so in this case, we need to consider we're doing a composite function here, right? We need to consider the domain of the input and the domain of the total problem, right? So I can't plug anything in if it's going to make g of x undefined, right? That if g of x is undefined, the whole thing's going to be undefined because I can't plug the number in. There'll be nothing to plug in. So what is my domain of g of x here? We got square root of x plus 2. What are we looking for with the square root problems? The radicand must be greater than or equal to 0. So if we solve that, that means x has to be greater than or equal to -2, right? We could just subtract 2 from both sides. So this is part of our domain for the whole thing. Because if we plug in -5, we're going to get undefined for g. And can you do f of undefined? No, you cannot. You got to have a number to plug in. So you're going to do the domain of the inside part first. Then we want to think about the domain of f of g of x, and then we'll combine them at the end. So domain of f of g of x. So we need to find f of g of x, which is where we take g and we plug it in for our x. So that's going to look like this, 1 over the square root of x plus 2 minus 5. Now, we already considered the square root, right? We thought about that one already, and we know x has to be greater than or equal to -2. What else cannot be true with this composite function here? This is a fraction. I cannot have the bottom equal to 0, right? So I'm going to take square root of x plus 2 minus 5 and say that that cannot equal 0. And then, even though it's a not equal sign, you can just solve it like an equation. So you'll add that 5. Get the square root of x plus 2 equals 5. What do I do to get rid of the square root? Second power. So that gives me x plus 2 equals 25. I subtract my 2. X equals, or cannot equal, 23. Now, sometimes that number matters and sometimes it does not. My domain of f of g of x, which I'm going to write right here in the middle, is going to be x must be greater than or equal to -2. But there's one other answer I can't have, right? I can't have and x cannot equal 23. I need to do that because is 23 greater than or equal to -2? Yes, right? It falls in the category that we are looking at. Now, what if that said x is less than or equal to -2? I wouldn't need to talk about the 23 because the 23 it's not less than or equal to -2 anyway. But because 23 is up here, like if we think of graphing this, we got, what happened there? -2. We got our 23. We're doing all the numbers. greater than or equal to 2, but 23 falls right there, and we can't use it because it's going to give us a 0 in the denominator. Okay, another way you might write this is the interval notation. It would be -2 to 23, parentheses, because we're not including the parentheses. You can use the union sign there, and then 23 to infinity. And you're using parentheses with both of those 23s to show it's not included. Okay, questions there? Domain of the inside first, then domain of the whole thing second, and then combine your answers together. Okay. Okay, this one asks us to describe the intervals on which the function is continuous. So, if I want to know where this function is continuous, I need to basically, I need to know what is happening right here with my x squared minus 9 over x minus 3. I definitely have a discontinuity at 3 in this part, and I need to see if it's fixed by this part. So, I'm going to do the limit as x approaches 3 of x squared minus 9 over x minus 3. And when I do that, what do I have to do? Factor it, x plus 3, x minus 3, x minus 3 here. I'm going to cancel. Okay, then what do I do after that, Avit? Once I've canceled, I got limit as x approaches 3 of, plug it in. What are we going to get for our answer, Avit? Good. Now, does that limit match the whole? The value that we have on that second part? It does not. So, I know f is not, I might should say like f of 3 equals 3. So f is not continuous at x equals 3. Is f continuous everywhere else? What type of function would that, I mean, this is just a single point. What type of function is this one? Rational. Rationals are continuous everywhere except for when the denominator equals 0, which is at 3, right? So 3's our only discontinuity on this. Now, the question doesn't say to, like, say it's continuous at a point or not. It says give the intervals where the function is continuous. So intervals where the function is continuous is from -infinity up to 3, and 3 to infinity is everything except for 3. Okay, questions there? Okay, I think we got one more. All right. 5 says for what intervals is f continuous? So, exponential, is that continuous everywhere? Yes. X to the third plus 2x, continuous everywhere? Yes. What about 5x over x minus 2, continuous everywhere? I see Raleigh shaking his head no. Where is it not continuous, Raleigh? 2. And is 2 on the interval we're using it for? Yeah, it's between 0 and 4. So there's a discontinuity. I know that. I'm going to write that down. X cannot equal 2. That's a discontinuity. What about cosine of 3x? Is that continuous everywhere? Yes, trig functions, even with the 3 there, are going to be continuous everywhere. So we got one discontinuity at 2 because of the equation, but the rest of the equations are continuous. What I've got to check is the pieces to see if they match, right? So I'm going to start off by looking at -1. I'm going to say this one doesn't say justify your answer. Technically, if it says justify answer, you need to be using limit notation. This is a long problem. The ones you're going to see on your homework are multiple choice on this one, so I'm not going to show all of that. So I got e to the -1, which is like 1 over e, and I've got -1 plus 2 times -1, which is going to be -3. Are those equal to each other? 1 over e and -3. No, because e's not a variable. E is a number, right? It's like 2.71828. So I have x cannot equal -1. That's a discontinuity. In fact, let me sort of circle those with a different color. So there's one, there's one. I've got to check 0. Okay, so if I plug in 0 to x to the third plus 2x, I got 0 to the third plus 2 times 0. That just gives me 0. If I plug 0 in here, 5 times 0 over 0 minus 2. That gives me 0 over -2, which also equals 0. Do I have a discontinuity at 0? No, those match up. So that one's good. Then I got to test 4s. So I'll do 5 times 4 over 4 minus 2, which will give me 20 over 2, which equals 10. And then I've got cosine of 3 times 4, which is cosine of 12. Do we know cosine of 12? We do not. Does cosine of 12 equal 10? No, because the cosine values are always between 1 and -1, so it definitely cannot equal 10. Plus, just the likelihood of it being a whole number like that's pretty low, even if you didn't remember that fact about being between 1 and -1. So those are not equal to each other. X cannot equal 4 either. So you got a lot to look at, but you're just running through and checking. Do I have discontinuities at all of these places? We got 3 numbers that don't work. For your final answer, you would go -infinity to -1, -1 to 2, 2 to 4, and 4 to infinity. I don't know what happened to my page there that made that crazy line. But so basically all you do is line them up. You're going to use parentheses for everything because that means you don't include the endpoints on that. Another way they sometimes ask this question is they make it multiple choice. And they might have 4 answer choices. They might have like answer choice A is -5 to 1. They might have B is 1 to 3. They might have C as 2 to 4 and D as 3 to 8. And they'll say on which interval is F continuous. So is F continuous from -5 to 1? No, because of -1 right there, right? That includes a discontinuity. That one's out. What about from 1 to 3? No. Which one's a problem? 2 is a problem. What about from 2 to 4? That one's okay. If it had brackets, would it be okay? No, but it's got parentheses, so it doesn't actually include 2 and 4. So that one's okay. What about 3 to 8? No, because 4 is a problem. So C would be your answer if it looked like that instead. So they may not ask you to like write out the whole thing. They may ask you to choose one of these that gives an interval where you'll be continuous. All right. Assignment for this is also on AP Classroom. If you get started right now, you might be able to get that one done before you go.